this video we're going to have an introduction to quantum mechanics. So we're going to see how we went from the Bohr model to the modern quantum mechanical model of the atom. So we talked before that one thing that the Bohr model got absolutely right was the idea that energy levels of electrons in an atom are quantized. The electrons are only allowed to have certain energies. Unfortunately, it only worked for hydrogen, and it failed when we tried to apply it to other atoms with more than one electron. Also, we now know that the idea of electrons moving in circular orbits was not the case. And so, this picture that we often see is not a correct representation of what an atom looks like. So, the quantum mechanical model is how we understand the structure of an atom. So one of the important ideas in the early development of quantum mechanics came from a French scientist, Louis de Broglie. And in his PhD dissertation, de Broglie argued, based on the wave-particle duality of nature that we knew for electromagnetic radiation, so going back to Einstein's work on the photoelectric effect, he said, if electromagnetic radiation can have properties of both waves and particles, could it be possible for matter, like electrons, that were generally thought to behave like particles, could they also have wave-like characteristics? And we now know in fact that they do, and this was key in the development of quantum mechanics. A few years after de Broglie's dissertation, the wave nature of electrons was demonstrated experimentally. And so this goes back to the double slit experiment that we talked about, proving the wave properties of electromagnetic radiation. And that's where if we had a light source and two slits, we could create a diffraction pattern. Right? Now, if electrons are behaving like particles, then we should just get two bright spots on the screen. We would not expect to see a diffraction pattern. But that's not what we saw. If the experiment is set up correctly, and they had to use atomic crystals to diffract the electrons, but they could actually observe a diffraction pattern from the electrons. And so this demonstrated definitively that electrons had wave-like properties. And it's not just electrons, but it turns out all matter has wave-like properties. And so we add on to the wave-particle duality of nature. Not only does electromagnetic radiation have properties of both waves and particles, but matter has properties of both waves and particles. And it's not just for electrons. The theory applies to everything. And so, you may say, well, when you have two twins walking down the street next to each other, they're not going to cancel each other out. They're not going to interfere with each other. We don't observe the wave-like properties of matter in our everyday lives. And that's because the larger the mass is, the less noticeable the wave-like properties are. So our wavelengths as humans, when we're walking down the street, are on the order of 10 to the minus 30 meters. So the wavelengths are so small that it's imperceptible. But as objects get smaller, as the particles get smaller, as the pieces of matter get smaller, the wave-like properties become more apparent. And by the time you get to something as small as an electron, it becomes vital to consider the wave-like properties if we're going to describe them correctly. And this is why earlier models of the atom didn't work, because they weren't taking into account the wave-like properties of electrons. And so when it became clear that electrons had wave-like properties, scientists already knew how to describe electromagnetic waves. And so if they applied some of the same principles to describing the behavior of electrons, could they develop models that accurately predicted the properties of atoms and molecules? And so some of the important developments came from Louis de Broglie, who we mentioned, who proposed the wave nature of particles. And then you may have heard of the uncertainty principle. That was due to Werner Heisenberg. And then the Schrödinger equation, which is sort of the equivalent of Newton's equations of motion, but for quantum mechanics, is due to Erwin Schrödinger. And so, as a reminder, sort of all of this goes back to sort of initially trying to describe the atomic emission spectrum. And with the development of quantum mechanics, we were able to do that, but so much more. in a very, very real sense, all of our understanding of chemistry can be tied back to quantum mechanics. Now, we're not going to get into the details of the uncertainty principle or solving the Schrodinger equation. That involves a lot of math that in general chemistry you haven't had yet. But in particular, if you go on to take physical chemistry, you'll delve much more deeply into the mathematics of quantum mechanics. So while we're not going to solve the Schrodinger equation, we are going to analyze the results of its solutions. So in the Schrodinger equation, we're essentially treating the electron in an atom as if it behaved like a wave. And for any given atom, for any given type of element, there are many possible solutions. And each of those solutions corresponds to a different energy state that that electron can occupy. And very similar to the Bohr model, the energy levels, the energy states of an electron in an atom are in fact quantized. Electrons are only allowed to have certain energies. And the way that Bohr described the emission spectrum, that the electrons were jumping between these different energy states, is exactly how we understand it in quantum mechanics. So that was something that Bohr got absolutely right. Now, a big difference between the Bohr model is electrons do not move in circular orbits. Because they are behaving like waves, in fact, we can't know exactly where they are. The best we can do is give a probability of where we're most likely to find the electrons in the cloud around the nucleus. And so, Bohr's model is sometimes described as the planetary model. So he called the paths of the electrons orbits. What we call these regions in space where we're likely to find the electrons in quantum mechanical theory is sort of a play on that name, and so we call them orbitals. And so an orbital is a region in space where we're likely to find a particular electron based on its given energy state. And so each of the solutions, each of the energy states in the quantum mechanical model is associated with a set of what we call quantum numbers. And you can sort of think of this as being the address for the electron, right? Like if you're going to tell somebody where you live, you would say, what street you live on, what city and what state. So the same thing is true for the electrons and these quantum numbers. When we specify these three quantum numbers, we're telling someone what the energy of that electron is and what region of space around the atom it occupies. And we'll look at these more closely in the next video, but just to introduce them here, the three quantum numbers are given the letters N, L, and then M sub L, M with a subscript L. N is called the principal quantum number, and it's also sometimes called the shell. This tells us about the size of the orbital, so how big is the region of space that the electron resides in, and also what is the energy. And the higher the value of N, the larger the orbital it is, and also the higher it is in energy. And so the values of N is it can be any positive integer. So 1, 2, 3, 4, 5, 6, 7, etc. And you can kind of think about the principal quantum number as being like the state. When you tell someone where you live, most of you, I assume, would say that you live in Georgia. But there are a lot of towns and a lot of streets in Georgia. And so the L quantum number is sort of like saying what city we live in. So N tells us we live in Georgia. L is kind of like saying, all right, maybe you live in Lawrenceville. L is the angular quantum number. Sometimes it's called the subshell. This tells us what the shape of the orbital is, and we'll look at the shapes in the next video. Now, the values of L depend on the value of N. So if you tell me what the value of N is for an electron, then there are only possible values of L. And L could be anything between 0 and N minus 1. Right? So as an example, if I told you that N is equal to 3, then the possible values of L are, it can be 0, 1, or 2. Right? It can be anything between 0 and N minus 1. Right? So in some sense, right, if we go back to our address analogy, if you tell me that the state you live in is 3, there are 3 possible cities that electron can reside in. The final quantum number, which we can sort of think about as being the street that we live on, this determines the orientation of the orbital in space. Right? And just as an example, one of the types of orbitals is called a p orbital, and it looks sort of like a three-dimensional dumbbell. And so the m sub l tells me sort of in which direction that dumbbell is pointing. Is it sort of, relative to the paper, is it straight up and down? Is it turned to the side? Or maybe it's coming, one of the lobes is coming out of the plane of the screen and one of them is going back into it. That's what we mean by telling us the orientation in space. And so just like the quantum number L depends on the value of n, the values of m sub l depend on the value of L. So, for example, if you tell me for a given electron that n is equal to 3, and you tell me that L is equal to 2, then m sub l can have any value that's an integer between minus L and positive L. So, if you tell me n is equal to 3 and L is equal to 2, then m sub l can be minus 2, minus 1, 0, 1, or 2. So it's sort of like saying, in the city L is equal to 2, there are 5 streets that electron can live on. All right, and so we'll explore this idea of quantum numbers and orbitals more in the next slide, the next video.